Hello. So in the previous example, we designed a 4-resistor biasing network for a discrete common source amplifier. And you recall what we did was to set the source voltage sufficiently low to have maximum voltage swing at the output terminal, that is the drain. So we set that to 1 volt. If we set the voltage at the source at 1 volt, for a 1 milliamp drain current or source current, we select RS to be 1K. So 1 volt over 1K gives us 1 milli and 1 milli. And then we need to select the gate voltage. That's determined by the voltage gate to source. And the voltage gate to source is actually the parameter that is going to control the current. So if we want a 1 milli, we enter it into the equation and we solve for voltage gate to source, which needed 3 volts, which means that the voltage at the gate needs to be 4 volts, and we could then design the voltage divider network, which we selected a 4 meg and a 1 meg to increase the input impedance of the common source amplifier to close to 1 mega ohm. So let's see if this works. Recall from the previous video that in order to do this in LTspice, we need to select the MOS4, and then we need to connect the substrate to the source terminal, as I did here. We include the model, the directive in SPICE, that model, give it a name, M1, and this is an NMOS. You enter the KP value, in this case was 50 micro, the threshold voltage, 2 volts, a lambda, if you are modeling lambda, in this case we were neglecting it, so but you could enter a value. And then we can do an operating point analysis. So let's do it. What do we expect? We expect the voltage at the gate to be 4 volts. Great. Of course, VDD is 20 in this case, so 24 volts. We expect the voltage at the source, we designed it for 1 volt. Good. And that will enable us to center the voltage at the drain. In this case, we have close to 10 volts. And the current at the drain, which is equal to the current at the source, because the current at the gate is 0 in a MOSFET, was 1 volt over 1K, 1 milli. You get there the 1 milli, which is exactly the same as the current in the drain. So this works. In the next video, let's connect the input at the gate through a coupling capacitor, the output at the drain through a coupling capacitor, and we have a common source amplifier. That is the gain stage with MOSFETs, which is equivalent to the common emitter amplifier for BJT technology. But in this case, we can see that even in the discrete case, we can increase the input impedance in the network because we don't have to worry about the impedance looking into the input of the transistor, which is in this case is infinity, as opposed to in the case of the BJT that will be beta times RE, finite. Thank you.